And the next, hello, we have the next talk online, another invited overview of the, in this case, the VEILS survey. Elham, Saremi, please go ahead.
Hello, thank you. Can you my screen? Can you see my screen?
Yes.
Thank you. Sorry. Hello, everyone. Thanks for organizing this great meeting. My talk is about the VEILS and VEILS survey and the introduction of a new friendly pipeline on VIRCAM for studying the low surface brightness structures that we are using for several projects of VISTA, such as KDFS, VEILS, and SHARCS. Here you can familiarize with our team. Ignacio, Johan, Helmut, and Zohre are working at the IAC and Mohammed at the CEFCA. Manda is the PI of the VEILS survey from the Southampton University. And I, in the end of the work at the IAC and starting the work at the Southampton University. As we got acquainted in the past few days, VISTA in the first 5 years of operations covered the most of Southern Hemisphere of the sky with the 6 large surveys with different depths. And in the next cycles, continued with some surveys such as VEILS, SHARCS, and K-band Euclid Deep Field South or KDFS. The VISTA infrared camera, VIRCAM, includes 16 independent infrared detectors. There are large gaps between detectors due to technical constraints. To obtain a full coverage of the field of view, at least 6 offset power print are needed for having a tile with the size of 1.5 cross 1 square degree. The VISTA Extragalactic Infrared Legacy Survey, or VEILS, is one of the VISTA surveys in the second cycle of surveys. As I said, PI of this survey is Dr. Manda Banerjee. VEILS is a deep J and KS band transient and wide field survey that was observed between October 2016 to December 2019. The main aims of this survey are to study the epoch of reionization, understanding the formation of massive galaxies, and studying of supernovae and agents. VEILS with 3 fields, XMM, ES, and CDFS, cover 9 square degree near to VISTA video fields. These fields overlap with dark energy survey and LSST deep drilling fields. So far, the first data release of VEILS is done. Images and single band and band merged catalogs are public through ESO, and all of the observations have been finished. The second data release is in processing. In the table, you can see the depths of quad images. They are proper for studying high redshift galaxies. Another survey in the second cycle of VISTA survey is K-band Euclid and Deep Field South. PI of this survey is Mario, and we are so sad for his loss. The LSST and Euclid survey will each deliver astronomical data sets over his decade in the optical and near infrared. Both surveys will map thousands of square degrees of sky from the ground and space, respectively, with an overlap area of approximately 9,000 square degrees at high galactic latitudes. The wide survey of Euclid covers more than 15,000 square degrees, and also Euclid has 3 deep fields that will be 2 magnitudes deeper than the wide survey. One of the deep fields of Euclid is named Euclid Deep Field South, covers 23 square degrees of darkest southern area of the sky, close to the south ecliptic pole, free of bright stars, with low galactic extinction and low stellar density, and huge potential for new exciting discoveries. The Euclid Deep Field South is also the 5th deep drilling field of LSST. Euclid will provide high spatial resolution near IR imaging in Y, J, and H filters. And this is while LSST will observe deep optical images, and this field is also in continuous viewing zone of JWST, ALMA, and WFIRST. In 2020, the Spitzer telescope observed this field at 3.6 and 4.5 micron, but as you can see, there is a wide wavelength gap between the Euclid and Spitzer data. A K-band survey can cover this gap. Detections of galaxies in the K-band can construct a comprehensive picture of galaxies population in the early universe. The K-band helps the discovery of galaxies at a redshift more than 2 that are faint at many wavelengths due to their evolved stellar populations and or significant amount of dust extinction. So thanks to all of these surveys by VIRCAM, we have a lot of near IR astronomical data. We know there are some standard pipelines such as CASO have for data reduction of VIRCAM's data, but do these standard pipelines of VISTA are proper for all of fields, for all of fields of astronomy, for example, for studying the low surface brightness structure. Truly none of the existing standard VIRCAM pipelines are suitable for LSP studies. As an example, you can see an optical image of the NGC 4030 spiral galaxy from STSS that is covered in the SHARCS survey by VISTA. And here you can see a K-band image of this galaxy from SHARCS survey that is released with a standard pipeline for VIRCAM. As Zohre showed in the first days of talks, you can see a standard pipeline how destroyed the outer skirts of the galaxy. Interesting not? We see a K-band image, however, it can be imagined that it is a UV image, that we didn't see any diffuse, while it is K-band, and we expect even less massive stars to be seen better. So this figure is not real. This is where we decided to write a new pipeline. Our pipeline is named Nasim, a Persian word that means a breeze. We wrote a fully automated pipeline that preserves a low surface brightness structures in the near infrared. First, let me show you the results of Nasim. Here you can see a comparison between the result of Nasim pipeline and a standard pipeline of VIRCAM for NGC 4030 galaxy. The differences are quite obvious, especially in the preserving the outer skirts of the galaxy. But how did we access such great results? Okay, in this pipeline, we used GenoAstro, which is an official Geno package consisting of various programs and library functions for the analysis and manipulation of astronomical data. With powerful GenoAstro programs, we removed most large flat patterns and large-scale instrument signatures in complicated structures of VEILS detectors, while preserving the LSP features in the final dataset. We used a non-aggressive technique for removing the sky. Here you can see the general structure of Nassim pipeline. It is written in 3 phases. In the first preparation phase, data preparation and validating of data are done. In the second preparation phase, we create metadata and then download images and categorize them. Then in the main phase, we redact the data. I'll explain more about this main phase in the next slides. All of 3 phases are done continuously and totally automated. Here you can see a raw exposure of VEILS in the K-band. In this image, we have a NGC, one of NGC galaxy, but the high background in the near IR does not allow us to see anything, unlike the optical. I have a simple flow chart for all of the steps in the main phase of the pipeline. Each exposure of our data includes 16 extensions related to 16 detectors. Here, I just added the name of GenoAstro's program that are used in each step. In a KDFS survey, there are 15 tiles of observation, and each one has around 20 nights of data. Generally, in one night, we have 42 exposures. So here you see 42 exposures in one night only for one detector. Removing dark images that, due to the high background in the near IR, can clean the image by just around 1%. Then we make flat fielding, which is the most complicated part of the LSP pipeline for the removal of instrumental structures, signatures, and gradient in the background. We don't use the twilight or dome flat, but we use science images for creating the master flat based on all of the images in one night, and for each detector, we create master flat and apply them to dark removed images. Now objects appear little by little, so we can mask objects in flat corrected images and dark removed images as well. With noise chisel powerful program of GenoAstro, masking is possible at this stage. And then after the to create master flats for the second time, in this level of pipeline, we experienced many challenges that I will explain a little later. We created master flats in this iteration as many as the exposures. Now you can see the appearance of a galaxy beautifully in this near infrared image. We use a non-aggressive sky removal in this step in spite of common pipelines because we don't want to lose anything. Photometric calibration and assigning weight to images are done at this level. We used 2 mask catalogs for that. First, we did aperture photometry by GenoAstro and matched our catalog with the 2 mask catalog. We have a limited usable range of magnitude around 14 to 16 mag because the stars that are brighter than around 14 mag are saturated in VISTA images, and fainter stars of 16 Mach are not complete in 2 mass observations. So for having more accurate results with better statistics, we collected catalogs related to all of images in one night. Okay, and for astrometry, we do it in 2 steps. First, we use a Solfit program, as Zohre pointed at the first day of talks. By creating a catalog of images by GNOAstro, we have full control over the inputs of Solfit. In the second iteration, we use a SCAM for the correction of distortions. To resample of data for the first time, we use ASTVOR program, which is one of the new programs of GNOAstro. ASTVOR calculates the flux value of each pixel on the new grid based on the mixing pixel technique. And finally, we have a final quad image and a weight map or exposure map. I will return to this galaxy at the end of my talk. And how do we manage these steps for tens of thousands of images? This pipeline is written in the manage. Manage is a framework for doing reproducible research. With helping manage, and the pipeline is a closed environment and independent of the host operating system, including all of the necessary libraries and programs for a fully automated process from downloading the data from ESO's archive to the final quadding and catalog production. From C compiler to high-level software such as LS, CP, Bash, and so on. To have a modular and clean architecture with the capability of parallelization and to have a high speed in such a large reduction pipeline, we are using GNOMake in this pipeline. All of the steps of processing from downloading data from ESO's archive to the final quadding using 15 cores takes less than 5 seconds for each image, which is impressive. Yeah, and also we have an optimized processing capacity that is necessary for working with big data. By decreasing 2.86 gigabyte of the required capacity for processing of each image, we can save a capacity of 755 terabytes in total images of the KS-band KDFS project for analysis steps. And we had many challenges to improve our work. For flat fielding, we tested many methods. First, we use all of the images in one night in both iterations of flat fielding before and after masking objects. We use all of the images in one night for creating master flat. Unfortunately, with this method, we couldn't decrease background ideally. Next time, we created several master flats in one night to decrease the effect of changing luminosity during the observation. As I pointed in the KDFS survey, we have 42 images in one night. In the top figure, you can see 4 master flats that are created with continuous images, and the ratio of them to 1 master flat that is created based on all of the images in one night. Changing the luminosity of the sky is clear, while a total of observations in one night is done around only 1 hour, but changing the luminosity is very rapid. Although this method was ideal from the point of view the background, due to not having proper dithering during the observation, we faced with problem of appearance of shadows around the big objects, as you can see in the this image. We tested other methods by replacing the values of pixels in two master flats, modeling of ratios, and many methods. Finally, we could decrease this effect with a new method for flat building. In this new method, we named it adaptive flat building. We created master flats in the second iteration, as many as exposures. Each master flat is created by 11 consecutive images. You can see that the result is very great. However, it is not possible for us to completely eliminate the effect of shadows for large objects due to not having a proper dithering during the observation for this method. As an example of results, here you can see the NGC 1494 galaxy from 2MASS. The galaxy I showed you in the pipelines flowchart. Yeah. The 5 sigma limit of magnitude is around 16 meg in the AB system. This galaxy also was observed in the VHS survey of VISTA and reduced with the standard pipeline. The limit of magnitude is 30 times brighter than 2MASS. And finally, you can see this galaxy as a result of Nassim pipeline in the KDFS survey. The 5 sigma limit of magnitude increased to 23.3 meg. And you can see the surface brightness profile for 2MASS image that I drew it based on the radial profile script of GNOAstro. The surface brightness limit in 3 sigma in 100 square arc seconds for a 2MASS image is around 23 meg per square arc second, while this value is increased for VHS image to 25.1 magnitude per square arc second, and there is a limit of 27.7 magnitude for the result of our pipeline on the KDFS survey, which is equivalent to around 30 magnitude per square arc second in the optical. The truncation radius is clearly visible in it, and I showed it with an ellipse around the galaxy. Here you can see a galaxy cluster in G filter for DECAM image. As we expect, we don't see any intercluster light here. In the I-band image, we see some intercluster light and more objects in this cluster. But if we check the K image as a result of KDFS survey, you can see the very nice intercluster light in the K band. Yes, we pick up the spectral energy distribution for a stellar population is around 1 micron, but based on redshift, that is around 0.7. Here we have the peak of SED around the K band. Amateur referred to many great examples of galaxy clusters in the near IR on Monday. Yeah, using the strength programs of GNOAstro, noise chisel, and segment, we could detect many objects in this cluster and see very nice intercluster light better in that. So you can see that Nassim pipeline is unique in the study of the high redshift universe in addition to local galaxies. Recording steps and creating order in each level of work is very necessary in each project. I documented all of the steps of this work in the Git server in the form of managed workflow. All of the codes and steps are committed, and how solving challenges is documented in the issues. This pipeline is nearing its final stage recently. Soon the related paper will be published. In the following, we have a plan for creating catalogs and ESO archives of data and building value-added catalogs as well. We would like to do a data release for the total KDFS, VEILS, and Shark survey, and archive the result on the ESO website. Here you can see an existing example of NGC 4094 archived on the ESO related to the VHS survey. This pipeline can be used for all of VISTA WordCamp surveys so that we can cover the total of South Hemisphere data for studying the LSP structures and so on. And it enables us to extend the LSST discoveries in optical. Now I am joining to LSST and VISTA Data Fusion project at Southampton University. The PI of this project is Manda. As Richard pointed out in his talk with more details, the main goal of this project is to process VISTA WordCamp near-infrared pixels through the LSST science pipeline to create a joint optical infrared survey data set in extended wavelength range from 0.3 to 2 micron. It can significantly improve the characterization of galaxy photometric redshifts and spectral energy distributions, and extend the LSST discovery space to the high redshift and low surface brightness universe. During the phase B of this project has made significant progress on the science pipeline. Raphael Shirley and Manda and our team. The HSC data was used instead of LSC data for the production of early prototype based on the joint processing with VISTA pixels. Because the LSST science pipelines are still rapidly evolving in phase C of this project, we intend to update the LSST VISTA pipeline to be compatible with the new LSST pipelines, and we ensure that deliver valuable data sets for scientific discoveries of LSST when LSST pixels become available. Thank you for your attention.
Thank you very much. Questions?